So yeah, I'll be talking today about measuring and reducing background velocity errors in phase contrast MR. So just kind of a quick overview of what our group does. Yeah, we're a cardiac MR group, so mostly exclusively looking at cardiovascular flow and motion, as well as cardiac mechanics and physiology. So we do a lot of kind of dense and tagging imaging to look at motion and displacement, to get strain. We do a lot of work in cardiac diffusion, which is a challenging process to just get everything fast and not be corrupted by motion. And then mostly what I'll be talking about is flow imaging, where we look at blood flow, either coming out of the heart or really anywhere in the body. And as far as our Skope system goes, we kind of have two sites. As Paul mentioned, we're kind of at Stanford, but also next door at the Palo Alto VA, where right before the New Year's, got us, so it's been 10 months now, maybe, have a Skope camera for our Skyra. We also have a GE probe too, which we aren't currently using, but have plans for in the future. So yeah, you'll see this project, which has been using the Skope in multiple ways. So first, some background about what'll be the main modality, in case people don't know much about phase contrast MR. This is a technique where we play out the kind of important gradient step we play out is this bipolar gradient. So it does no spatial encoding because it has zero sum. It's kind of a positive and a negative lobe. But what it does do is add sensitivity to velocity in the form of phase. So when we acquire one of these images, which is just a standard SPGR image with this bipolar gradient added, what we get are kind of standard, spoiled gradient echo looking magnitude images. But then if we look at the phase data, we'll see that our phase ends up proportional to our velocity. It's a kind of direct linear mapping. And here you see this is just a scan at the top of the heart, where you see kind of blood coming up out of the ascending aorta, and then you can actually the next most important vessel is here, which is the blood going back down the descending aorta. So if we want to measure data in phase, there's one extra processing step that needs to be done, because there's phase coming from lots of different things in the image. So to get rid of a lot of them, what we do is actually do two acquisitions. So every time we acquire one line of k-space, so here I'm just looking at the flow encoding direction, which in this case is going to be the slice select direction. So all these images are kind of 2D images, and we're measuring flow through the plane. We can actually change that if we want, but this is by far the most common. So we play these bipolar gradients in the slice select direction to measure flow in the slice select direction. But if you acquire just one of these images, what you would get is something like this, and you'd see a lot of, it's hard to see because most of this is air. So when you look at noise, it looks like the salt and pepper noise. But if you look at static tissue, you'll see there's some non-zero phase. This should be gray. This comes from lots of sources, chemical shift, off resonance, and things. And so because of that, we need to do a second acquisition that with everything else the same, but a swapped bipolar gradient, so that when you subtract them, you then can subtract out most of those phase errors. But because you changed the flow encoding between them, which is denoted here as the gradient first moment, but that's not super important, then you can subtract the two and get an image that's not as corrupted by all these sources of phase errors, and get something with the phase that's hopefully much more related to only velocity and not other errors. And so, as I said, this phase subtraction removes a lot of phase errors, but particularly it's only removing phase errors that remain constant between these two TRs. So the big ones and that we need to get rid of are things just like B0, shifts that are off, chemical shift susceptibility, and inhomogeneities. And those can all be subtracted easily with this because they just stay the same between those 5 milliseconds that you're looking at. However, because we need to change the flow encoding so that we don't subtract out the flow encoding too. Any errors that are caused by those particular bipolar gradients, because they're being reverted, can actually get doubled instead of subtracted. And these are then generally we consider them to be the concomitant fields, gradient nonlinearity, and eddy currents. And we have corrections for concomitant fields. Those are the Maxwell terms. Those we just know analytically what the answer is as long as we know our gradient waveforms. And gradient nonlinearity too, the vendor supplies maps of that so we can kind of undo the effects. But the more troubling one to correct are eddy currents, which is going to be the main focus of this talk. And so what these do is, yes, so these phase contrast bipolar gradients create eddy currents and mechanical oscillations that then create background phase. And these lead to velocity errors. So if you look at this as a picture through the liver, once again, capturing the aorta and then vena cava coming up, or yeah. What you'll see if we kind of just look at the standard velocities is you don't see much, but if we kind of window level and look at kind of low velocities, you'll see that all throughout the liver and the body here, you see a lot of measured velocity that's not real because these things aren't moving. And so this is really the error we care about. It's small relative to the measured velocities that we care about, but it's because generally we're looking at net flows, we're summing this over time, and it's like this constant bias that can actually cause pretty big errors, up to like 20% of a measurement. And it's still a big problem in phase, or a decent sized problem in phase contrast MR. There are corrections already. So this is generally dealt with retrospectively with polynomial fitting. So if we can either manually or semi-automatically pick out tissues we expect to be static, we can then fit a low spatially varying field to that and just subtract it out. And that works pretty well. It has some problems in that, yes, some cases, so in the chest where you have just mostly lungs, if you're measuring the heart, you might not actually have much static tissue to get a good fit. And that happens somewhat frequently. We also have like wraparound artifacts, or if you have GrOpt artifacts, when you're trying to do this spatial fit, you're trying to fit pixels that aren't actually where you think they are into this fit, which can really throw things off. And the other real problem with this kind of retrospective fitting is that it's because these fields are so small, it's often not clear. It can happen that the correction doesn't go well, and it's not readily apparent that it's happened. It's not this glaring error. And so that's also a problem too, reliability of just how often this is actually working properly. And to be fair, though, in general, I would say this probably works, 95% of the time. It's just these problems that these cases where it doesn't work are kind of hard to catch. And so it's still a big problem because of that. There's also been some recent, kind of similar to what we're doing, but using a different method. Also other attempts to do this in a perspective way. So kind of looking at the mechanical resonances that I'll talk about and just kind of picking TEs and TRs that might work best with those resonances. Okay, so this is some of our first field camera measurement stuff. So this is just kind of a really simple experiment looking, just using the Skope camera and playing a bipolar. I put the trigger here. This line is not the trigger. That we trigger somewhere over here, measure the whole waveform. This red line is just for reference in these two images to see where the bipolar ends. So if we look at just, let's say, two components of the field we're measuring here, you can see the B0 component and the BZ component, so the same gradient here. If we maybe look at the gradient first, you'll see I'm kind of cutting off the bipolar. In this instance, we don't actually really, so if the bipolar is a little bit wrong because of errors or eddy currents, that's maybe a little bit of a problem. It's going to change the flow encoding a little bit, but it's unlikely to be more than a couple % or something. So that's not actually as big of a deal. What we care about is kind of what's going on during the readout, because basically wherever the TE hits, whatever the background, whatever these eddy currents are, they're going to turn into that background phase. This is what's causing the error. And so, yeah, what you can see from this is that we definitely have noticeable fields here. They're not particularly big or anything, but they're big enough to cause our problems. We also just qualitatively, you can maybe pick out that they seem to be mostly related to mechanical oscillations. Yeah, generally we're seeing things, in the, I think, where a lot of people see them in the 1 to 2 kilohertz range. Maybe 1 to 3 kilohertz range. Yeah, where we see, and these just correspond to acoustic resonances that we've measured before. So it seems very clear that they're mechanical oscillations. We don't even really see that much kind of exponential decay-based effects, probably just because these gradients are so short and they're perfectly balanced. All these kind of long-term decay terms are probably canceling themselves out, so it's mostly just the mechanical oscillations left. And so, yeah, this is a problem trying to figure out exactly what we can do about this. And other groups have shown this before, actually, with field cameras as well. So this was a case of just measuring it and characterizing it, showing measured fields here with the field camera, kind of looking at the spatial or the frequency components of this, where you can kind of pick out these mechanical oscillation peaks and just kind of a general oscillating behavior. Where if you pick, and this is kind of related to the work of the other group that I was talking about just basing this and not really changing waveforms or anything, just trying to find TEs that might fall into the smaller regions here. So our goal, rather than kind of changing the TE by a lot to try to find a place to play anything or changing the timing, can we make our velocity encoding gradient or just change any of our gradients to produce less phase error? But before that, the step I'll get into is that, so if we want to do this prospectively, we can't just be measuring and correcting the field with the field camera. We need to be able to predict the response a priori. The way we're going to do that is to use a gradient impulse response function to predict these extra fields that sum into the background phase. I'm guessing a lot of people probably know this already, so I'll just do a really quick overview. But basically, the really simple explanation of what a GIRF is it's just a kind of function that we convolve with our programmed gradient waveform. So this H term here is the GIRF. If we know the gradient waveform that we programmed, we just convolve them and get a measured kind of actual field that we're going to measure on the system, or what's actually happening. And this can have different spatial components. So we'll normally compute a GIRF for kind of a 0th order field, and then kind of linear and higher order terms. Yep. And so how this actually works for phase contrast imaging. So what this looks like, so this is going into what the standard phase contrast sequence looks like. I showed the waveform before, but I'll just go into a little more detail. And these blue ones are obviously, I mean, it's all standard SPGR, but so we just have a standard slice select, then we play these bipolars, then we have a spoiler. And on the other axes, we have just standard readout and phase encodes. And this is then just showing 2 TRs, the only difference being the flipped velocity encoding gradients. So what do we need to do to predict this? So I mentioned, obviously, we predict the field with the GIRF. So we take this and we convolve with the GIRF. In this case, this is just for the 0th order field. This work will actually all do the 0th order. I'll mention at the very end, it's kind of a preliminary step. Ideally, we need linear terms too, because these higher spatial order terms can affect our flow measurements. But the kind of biggest culprit is the 0th order term. So we kind of have just addressed that alone first for simplicity. So we take this program gradient waveform, convolve it with the GIRF, and we get some predicted 0th order field. And here you can see it's pretty complicated. It's you got a lot going on during the gradients, but yeah, mostly seems to be oscillations. This alone doesn't tell us the background phase, because we need to kind of replicate some more of the processing chain that goes on in phase contrast imaging. So first, obviously, this is just the field here. What we actually care about is the phase, right? And that's the summation of the field from excitation to wherever we are in time. So that's kind of the first step. Is, I mean, yeah, obviously simple, but just taking from excitation and kind of having a cumulative summation from that point to give us the phase of an individual TR. But then there's another step. So this actually isn't that step. We then actually do that once for this TR and then once for this TR. So we basically take the phase summation from this TR, subtract this phase summation from this second TR, subtract the two, and then that is our predicted background phase. And then we can convert phase to velocity, because it's just, as I mentioned, just a linear term based on the gradient first moment. And so from that, we get this curve, which is most important. So we put in a gradient waveform and we get out the predicted background velocity at any given point. Well, then for a lot of this, because we'll find prospectively, we can't really get rid of all of this, because that would be getting basically rid of all our mechanical oscillations and would probably make a silent scan, which would be nice, but doesn't seem possible based on what we've tried. What we instead do is pick some region that we care about, because these background velocity terms are very low spatially ordered, or very low kind of spatial frequency content. They're always smoothly varying. It's generally the only part we really care about is what we're measuring right around the TE. So, a couple K-space points around the center of K-space is what's really containing all of this error. So what we'll focus on then is just whatever the measured velocity or measured background phase is in a small window around the TE, which is this kind of red window here. So yeah, we have this, we have the GIRF. I'll talk about how we measure that a little bit more, but yeah, so we have this GIRF. We have an idea for how we can use it to predict the background velocity. We then wanted to test it. So we came up with this experiment where we kind of just scan a phase contrast image at a range of TE values, just measure the background velocity and compare it to what the GIRF predicted. So what this looks like, once again, the same sequence I've been showing, standard SPGR, we got the bipolar here. Basically, the only variation in this experiment compared to a standard phase contrast exam is the TR is a little longer to make a big gap here in kind of the readout area. And then what we do is keep running the same scan over and over, but just shift the readout. So we have an image at a bunch of different TEs. We actually end up doing about 40 TEs here, all just really only like 40 microseconds apart. So just lots of images with slightly different TEs, but all the same other timings. So we should still have the exact same response, because while these gradients, all these other gradients are creating their own eddy currents and things, we've found from testing and just theoretically that because those gradients all stay constant during the TRs, they end up reaching some steady state and all getting canceled out by that phase subtraction step. So really all we are going to care about is what's happening due to the bipolar gradients. Okay, so what this looks like is we play this gradient waveform and we get, as I mentioned, those 40 images. In this case, there's just a spherical phantom in the scanner. And so we do each of these TE images, each get their own reconstruction, and then each one, we look at the background phase. So we kind of window level really small on the velocities and see this. And so you can see, we can then actually, for each individual image, we can just do a fit on it to see what the 0th order term is and all the other order terms. And we can basically just make this plot. So for each time point, we have the measured background velocity. So this one goes here, and then it starts going positive and then negative here. And so you can really also just see directly in the imaging experiment, you see these oscillations as well. So now what we really care about then is to take this and go back to what the GIRF predicted and see how well it matches up. And so this is the field, the field and the predicted background velocity that was measured with the GIRF. And you can see it's matching up pretty well, though maybe not perfect. It tends to be worse by the bipolar, right after the bipolar, and gets a little bit better. But yeah, so good, but maybe not perfect or anything. So we did this first, and then obviously we wanted to, get the prediction as good as possible based on what we're actually seeing. And so then kind of in the middle of this experiment, we got our Skope camera. So what I actually just showed you was kind of a pretty sophisticated method of doing the GIRF, like with higher spatial order terms. It's from this paper here, but it's a kind of 3D thin slice method that takes a while. And so, yeah, that was the kind of thin slice GIRF. We then got a Skope, and basically with the kind of exact same test waveforms we did with our thin slice based GIRF, we measured it with a Skope. It was obviously much quicker because we just measured once. We've actually tested, doing longer, and really it doesn't seem like noise is a problem. It wasn't actually needed. So yeah, we can do it really quickly with the Skope. These were both required different times from the imaging study, so if there's some drift, that might still be a source of error. But yeah, and so then, and I'll delve into the actual numbers of this a little more, just kind of qualitatively. You can look at, if we take that thin slice method that I showed before, we can also compare against the Skope, and you can see, at least in this one example, the Skope seems quite a bit better. Still not perfect, but definitely the GIRF measure with the Skope is matching up much better. Yeah, So with that, it really does seem that the GIRF can be used to predict the phase contrast background phase. And that itself could be used as a correction method. I mean, if we just know what the background velocity is, we can just subtract it. There's still some problems there with especially the fact that if you're sampling a point that's kind of has a really steep slope, you can pick the TE point, but on either side of the TE, you still have some field that's going up and down that might be a little harder to correct. And also, yeah, if you're sampling at a point that has a really high slope, you might just, even if you're off a little bit on your timing or something, you could still maybe get too much error. So we wanted to see if we could prospectively correct it. So make gradients that within a whole window region are below some threshold of background velocity. So yeah, it's just what I said here. Yeah, can we just use the GIRF instead of just using it to predict? Can we actually prospectively reduce the error with that? And so to do this, we designed, we tried to change either the bipolar and or the spoiler shape with a gradient optimization framework called GrOpt to do this. Just a quick 2-slide summary of this. This is so the idea of gradient optimization has been around for decades now in various forms. The idea is that rather than just using kind of analytical traps and shapes like that or triangles, you just use numerical optimization to find some gradient waveform that satisfies all the things you care about. So things like proper moments for like encoding. Let's say you're doing a phase encode, you just need some area. You need to make sure you hit that. Or spoiling, you need some area. With flow encoding, we need a certain first moment to get the right velocity encoding. But other than that, you don't apply any constraints on shape or anything. So you can kind of maybe get more interesting or maybe faster waveforms. And so we have a kind of software package that's a very flexible way of doing this with lots of different constraints. So we've also used it a lot for diffusion, kind of using all the same waveforms and actually other sequences as well, other SPGR and TSC, some TSC sequences at some point. But in this case, basically what we're doing is we're going to have moments, the constraints to find a waveform that hits our velocity and spatial encoding, but then also try to just let the optimization try to find some waveforms that produce a predicted background velocity in that window that's below a certain amount. Basically exactly what we want. We set some cutoff based on basically clinical standards and some papers that have suggested a good clinical cutoff, which was either like 0.5 or 0.6 centimeters per second. At least in cardiac imaging. And so we compare to that. And so we've done this. This is kind of some examples of what this looks like. So this is a sequence here. You see here the reference sequence that we're basing things off of. You see the 2 TRs, and then you see the predicted background velocity. And this is the TE right here in this red bar, and you see the predicted velocities, maybe about -1 centimeters per second. We then kind of formulate the problem in a couple different ways. Mostly the difference between these then 3 other panels is that we're just kind of, we're testing out which gradients maybe make the most sense to optimize and try to change to get this to happen. So one is to change these bipolar gradients. This is the velocity encoding. So you can see we get some kind of weird shapes here. It's maybe not always clear exactly what or why is going on because that's just how the numerical optimization works. But what we do find is that, it has all the right velocity encoding, it has the right spatial encoding, but then also this predicted background velocity here, you can see is much smaller and is 0 in the region we care about, or close, below that threshold we set in the region we care about. Another interesting way to do this would be with just the spoiler gradients. So these oscillations last a while. So when we do these optimizations, we're actually kind of looking at a steady state. So we're kind of not just looking at 2 TRs, but assuming we played a bunch beforehand so that we can kind of estimate, what the steady state, or it's maybe not necessarily a steady state, but basically what's happening closer to the center of K-space after you've played a bunch of TRs. So basically the spoilers from the gradient before are still affecting, the eddy currents are still around, those oscillations are still happening. So we can kind of use the spoilers from the TR before and even TRs before that, because they're long lasting, to affect the predicted field. So here you see one where the bipolars aren't changed, just the spoiler gradients are. and that creates this predicted background velocity field, which is close to 0. And then we have one where you actually allow both to be freely modified. This is one where then the optimization didn't actually need to do much with the bipolars because the spoilers could really do everything. And one point to point out here is that this isn't free. So these, well, in actually one of these cases, it is free, but that's just kind of something that happens because of the way the sequence is set up. But these bipolars can't really get any faster and still hit the same velocity encodings. They're already the kind of time optimal fastest we can do. So if we want to have them do something else, in this case, minimize background phase, they need to be a little bit longer. So when we optimize bipolars, we're increasing the TE and the TR by the same amount. And so that is a small problem. I will say throughout this entire project, all the waveforms and things you've seen, the biggest gain was only 0.2 milliseconds. So these are very small increases in time that are needed, but it does increase the time a little bit. And similarly, the spoiler would need to get bigger. In this scan, we're actually comparing it to a Siemens reference scan that also has spoiling in the readout, which actually took more time. So actually, technically, none of the spoilers added any time to the sequence. That's only because there was another spoiler that needed more time. So it didn't need to be time optimal. But yeah. So yeah, you can see just based on the prediction only, this seems to be working well. Though, of course, to test this, what we do is actually put it back through that sliding TE experiment. Here we kind of change the phantom to this gel body-like phantom. So here you see that same sliding TE experiment that I showed before. There were still kind of 40 TEs. I'm only showing 10 of them. And what you see here is not actually the 3 optimized ones I showed before. This is 3 bipolar and spoiler optimizations. Instead here, what we're doing is changing where this window is. This was just kind of a proof to ourselves to show that we can kind of arbitrarily set that. So let's say you change like the asymmetric echo and your TE position shifts. You can really kind of arbitrarily pick what point to put into the optimization should be minimized. So this is just looking at 3 different temporal positions to do the minimization at. They're highlighted in red, and you can see that it seems to work well based on these images. All the images where we intended to minimize are minimized. And then this is similar to what I showed with that Skope versus thin slice GIRF example. This is the same kind of figure where we're looking at the sliding TE measurements in dots here. And then this is then the Skope GIRF predicted in the blue. And so you can see these are just kind of the reference exams with 3 different window positions, and then the 3 different methods of optimization. So bipolar, spoiler, and bipolar and spoiler. And what you can see from these is that the prediction is lining up well with what we're measuring, though once again, still not perfect. You can see maybe this one's probably the worst, or maybe right here is the worst. So we can still get some decent sized errors, but in general, it's working very well. All the regions we care about, these red regions, you can see the dots are falling below these dotted lines, which is that clinical threshold I set before. So yeah, so really in all these examples, it seems to be working very well. We can design these waveforms that match up to their prediction, and that prediction is having 0 background velocity where we care about, which is kind of exactly what we wanted. Okay, so now just taking a quick kind of aside. So once we have all this data, we can look at the just kind of, the root mean square difference or some measurement of the error between the predicted and measured, and use that to do some characterizations. One of the characterizations we did was just looking at which GIRF we should actually be using to try to see what fits best. And so there were kind of 2 dimensions to this comparison. We first compared that original thin slice GIRF method to our Skope camera. And we also looked at a bunch of different kind of test waveforms to see which one might work best. So maybe I'll talk about the waveforms first. So the waveforms we tested, there's the kind of standard GIRF is to play a bunch of blips. This is nice. They all have a nice sync profile. And when you do a couple of them, all the lobes of the syncs hit the places you missed in the other blip. And so it gives you a nice frequency characterization. The problem is there's just not that much signal here. They're kind of small. So this is kind of the standard way to do impulse response characterizations, but from a just kind of SNR time perspective, it maybe isn't optimal. We also did kind of the same thing, but with bipolars. I've never seen this done, and there wasn't a great reason to do this other than we're using what we care about our bipolar gradients. So maybe measuring a GIRF specifically with bipolar gradients might be helpful. So we wanted to test that out. Another waveform that's been proposed is kind of the chirp waveform. This sweeps across a frequency range. It's nice as compared to the blips in that it has a lot more signal for a given waveform. Obviously, if you look at the timeframes here, they've shifted so that you have a lot more gradient to measure here. We also tried the pseudo-random method. This was something we had just in place actually for another project, similar GrOpt project where we were measuring acoustic responses. So it had been proposed in some paper about measuring acoustic responses. I had never seen it done for a GIRF, but I just had the code, so we tried it. And so yeah, if we look at that, either with the thin slice or the GIRF, you see kind of in that order I mentioned, everything gets slightly better. The chirp and the random waveforms, because they're bigger, we did see and just have more signal. We did, or presume that's our, at least our prediction of why it's better. Did seem to perform better. This randomized waveform did seem to perform a little better, though it wasn't actually, it was not significant in either of these. So both the chirp and the random waveforms kind of performed mostly equivalently. And the other thing you'll find is that just in general, the Skope performed much better. I mean, the error was like half or smaller than half when we look at the prediction versus the measure. And then, sorry, this last one was it's just that we just summed up the responses from all of these and just combined them all. And eventually that's what we use, is just because we had the data. I think in the future, if we were doing this, we would probably maybe only do chirp just because it's maybe the accepted way, or this randomized one. But right now, because we have it, the kind of GIRF from all these responses you're seeing are all these results are the Skope camera GIRF with all the waveforms. We've also, so everything I've been showing is axial so far. It's kind of the easiest, right? Because these GIRFs are actually different for coils. So when you play green on the Z, you have a different response, obviously, as when you play it on X or Y. You have different GIRFs. But actually, it's not very hard to do obliques with this method either. We basically just take our GIRFs kind of in the physical coordinates, so on the XYZ axis, take whatever our given oblique slice orientation is, and basically get GIRFs in basically image or logical coordinates, whatever you want to call them, and then still just use the slice select GIRF from that kind of rotated system. And what we found, we did, kind of sagittal, coronal, and oblique slices from that same phantom, and I won't show all the curves, but we saw similar results. Though I would say actually not completely similar. The X and Y GIRFs do seem to be a little bit worse at prediction, and we don't actually have an explanation for that, if that's well known or not, or just something we're finding. But still, it's always been good enough to kind of hit our thresholds that we care about. Yes, so that was kind of just another aside on what we're doing with oblique slices. Yet another kind of quick aside on another project is a kind of direct measurement of the response. So yeah, we've talked about looking at using the Skope just to kind of understand the fields with a simple bipolar, using the Skope for a GIRF. We've also tried to use the Skope directly in, the full phase contrast SPGR sequence. Basically just, we've played a bunch of TRs before this, then we're on this TR and we put a Skope trigger. We put a trigger here and just let the camera record during the readout. And then, of course, we need that TR subtraction. So we have to run it on a separate scan or another scan later to trigger and get a longer one. And here we see also good agreement with our kind of predicted velocity. So this is the Skope, or the actual measured Skope field in blue, and then that sliding T experiment. We see good agreement here, though it's not perfect. There are some problems with this experiment relative to the GIRF. One is that, so as I said, that when we do that TR to TR quick subtraction, we're maybe getting, because we're immediately subtracting stuff out, we're maybe getting rid of things like B0 drift. It's not drifting in those 5 milliseconds. But currently the way we're set up, I think we can do this better. This Skope measurement, when we measure one TR, we're measuring for one sequence, and then we're waiting for a relaxation and grabbing the next TR, maybe like 5, or maybe it's even like 20 seconds later. I forget how much later, but it allows for some more drift that normally wouldn't happen in a sequence. And so that's probably why it's happening. But even without that, this is, so I'm showing the subtraction here. It's actually been very useful for kind of single TR comparisons, because that's another step in the prediction, that before this phase subtraction, we're predicting the actual single TR phase. And so we've been able to use that to kind of help us figure some things out. So that's been very helpful too, to put the Skope measurement directly in the sequence we're measuring. Yeah, so the last thing I'll talk about, I think I'm running short on time anyway. I'll also go through, it's only a couple more slides, is we tested this in 5 healthy volunteers in the liver, heart, and neck. So just 3 different slices, kind of with all the GrOpt optimizations I've talked about. Here's just some velocity images of kind of what we're looking at, the cart and the chest, the liver, and then it's kind of low on the neck, but also looking at flow in the carotids. If we compare flow, we see good flow values. You see some different voxels, but this is actually kind of standard usually seen in kind of back-to-back scans, even with phase contrast. There's just lots of beat-to-beat variability. So the kind of flow differences between the optimized sequences and the regular sequences are all within what we would expect. Good agreement between flow curves between the different optimization methods and the conventional. And then if we kind of zoom in to the background velocity, you can see kind of the uncorrected here. These start getting a little bit noisier, but maybe, and I'll show you the actual measurements later. But so here you can see the background velocities and how that's kind of getting smaller, and with the 3 different optimized methods. And if we actually characterize what the background velocity was from these images, we find that in all the cases, the reference one is much higher than the optimized ones. The optimized ones all, really except for one image, hit our clinical thresholds. So yeah, once again, not hitting the perfect 0 we'd expected, but whatever error is left in our prediction not hitting is good enough to stay under our clinical thresholds. So yeah, in summary, it does seem that these GIRF predictions of eddy currents can be used to prospectively design a PC-MRI sequence with minimized background phase. And what we also found is that we've kind of switched to a GIRF measure with the Skope camera because it definitely better predicts this response for us. The kind of some of the remaining questions we have is kind of we don't think it's like an SNR problem with our GIRF from the Skope, and we think the GIRF is as good as we can get it at this point, or maybe not quite. There might be some better test waveforms. Some other people at Stanford have been working on that. But yeah, just kind of trying to figure out why we can't predict it perfectly. It also just could be nonlinearities. It seems like in these kind of GIRF prediction things is always the response. So it could also be just the nonlinearities that aren't being picked up by a GIRF. Also, a big concern here is the temperature dependence of the GIRF. So we're doing all these corrections based on the GIRF we measured. And most of our experiments were coming into a kind of fresh scanner. But people have definitely shown that the mechanical oscillations change frequency slightly, even when the gradients start warming up. And so the question that we haven't fully tested is just how well this is going to work. We're presuming all of our results that I've shown here are kind of a cold system, but how well this will work on as the system warms up and the GIRF changes. Our optimization framework actually, and we've actually tested this a little bit, allows for us to kind of have a cold and a hot GIRF and try to find a waveform that would optimize for both of them. It might require a little bit more time on the gradients or make the gradients a little more complicated, but it's definitely possible. So we have some solutions for that, but it just hasn't been tested yet. And also a problem that we just still haven't remeasured. We kind of know about it is that those acoustic resonances that seem to be dominating our error, from what we've heard and talked to other people, they last a long time. So our GIRF measurements are only measuring maybe 30 milliseconds. And these oscillations might be lasting on the order of like 100 or more milliseconds. So it could be another source of possible error is just that we're not kind of accounting for how long the mechanical oscillations are going for. Yeah, and so that's it. Thanks.
Thanks, Mike. Anyone in the room have questions? I can relay the question as well. Jumping?
Yeah. Yeah, good luck. Thank you, Mike. Questions of the phase imaging. So you just mentioned even one of the zeros. Question is how about the higher order?
So
field changes?
So Jumping is asking about the higher order field changes. You mentioned linear, but you've started with just the center frequency or B0 term.
Yes, so we've done like a really preliminary test where we've minimized the 0 term and then also just add a constraint on the linear term to minimize it. And that does work. It requires a little more time, and we just haven't tested it as much. We've also done a test where we've even like increased the linear term just to kind of prove that we have control over this, and it's working. In general, at this point, it was just like this project was getting so it's not that we can't do it or really have any problem doing it. It's just that it was getting so complicated to tease out all the effects that we've kind of left it out. But we do have preliminary information data that we can do it just fine. It requires a little bit more time. As I said, like all these have a penalty for how much extra time you need, how much bigger the gradients might need to be. But it was still only like a fraction of a millisecond. So it's doable, yes. And we've done it already, at least as a test. But we just haven't thoroughly investigated how well it's actually working or anything. But yeah, and it's definitely important. I mean, you could hope that because we're defining everything at isocenter, most of the vessels we care about are going to be at isocenter, so the B0 is maybe good enough, but all the literature on, let's say, the polynomial corrections say you need at least a linear fit. So I do think I would say it's not complete without having the linear term as well. It's just, yeah, it just wasn't in the scope of how we decided to do the project right now. So like really, we just wanted to like pick one to get as good as we can and then add linear after. So that's kind of where we're at.
Well, so I think so the basic imaging is also sensitive to higher order.
So Shopping's asking about something like second or third order terms as well.
Yeah, we could do it all. I mean, we haven't tried it all. The question is just like, as long as our measurement and we can make the GIRF from all of them. Basically, the process is the exact same for the GIRF. You plug in the gradient waveform, you plug in your measured fields, and you just do a deconvolution. You do some like Wiener deconvolution or something. Yeah, we're doing a Wiener deconvolution. So you really just your measured field. You can plug in anything the scope spits out to make a GIRF from your gradient waveform to that field, and then use that in our framework. We can kind of add. Oh, go on. Sorry.
I think Mike. I think I misrepresent Shopping's question.
Oh, sorry.
That's the question three. So I think my question is several. Because I'm not a guy in operations, so I think my question is more like, so since a phase imaging is also sensitive to higher orders, right?
Sorry, I couldn't hear that completely.
I'm missing the question again.
So the phase imaging, it's also sensitive to phase errors arising from higher order terms.
So phase imaging, yes, is also sensitive to errors arising from higher order terms. I think that's the question. Yeah.
And so this could be helping with that, especially if we start adding the higher order terms. Yes, I mean these higher order terms are causing other errors besides just background velocity too. Maybe is what you're getting at. And actually, one of the reasons we started this project was because we had some like 3D cones flow experiments where, yeah, we thought not just background velocity, but actually like trajectory errors and things were happening during the readout because of the bipolar gradients. This might help with. And so, yeah, I think that would help there too, doing these higher orders. And this kind of methodology, I think, yeah, any type of phase imaging could be useful as well. I mean, we talked about like fat water for this as well. So yeah, maybe that gets closer. I don't know.
So another complicated question, you mentioned the thin slice method for GROP measurements. Are you talking about Jeff Dunn's?
He's asking clarification about the thin slice method, whether or not it's Jeff Dunn's.
It was from Phillips people. I honestly forget the name. It's basically what we do. I know that I can
Reiner and Horner. So yeah, it's an extension of that thin slice method to get a spatially resolved.
Yeah, so basically you actually do like phase encoding. So yeah, you do basically 5 slices, and then each one you actually do 5 phase encodes. So you get a super low resolution, like quote unquote image of the response, so that you can get some spatial terms. We've only actually worked with up to the linear terms on it, so we don't actually even really use it, the higher order stuff.
So your measurement with Skope, how many output channels did you have to have?
How many what?
How many output channels? You mean like how many different GIRF terms they calculated?
Yes.
Yeah.
So we have them all measured. I didn't even know you could turn any off or anything. So we just have whatever the default measurements would be, but we've only used mostly the 0th order, as I mentioned, the linear. We have the other ones, but just haven't even looked at even the prediction yet. I mean, it would actually be pretty easy to just test how well it's predicting things. Like I mentioned with the sliding TE, we already have all the data and we could remake the GIRFs. It's just something we haven't looked at yet. So we have at least everything there to make basically all the GIRFs that the Skope measured. And with the thin slice method, we could do the same thing. I think you can solve up to higher orders. I doubt it's very good above second order, but yeah.
Okay. I have one brief question, and it's leading because the group here will go this afternoon to the 10.5 and we'll do a demo showing how we acquire GIRFs. And one component is you've been talking quite a lot about either self terms, so like GX to GX. So what does GX do when you pulse it? But then there's also these cross terms, like what does GY do when you pulse GX? Has any of that come into your consciousness as well for this type of work as well?
Actually, yes, that's actually all we care about with this for the linear term. So actually I showed it here, but this linear term we actually don't care about because this is just going across the thin slice and it's maybe affecting your velocity slightly, but it's in general we're at like isocenter too. So actually what we do care about is when we play this, like we're encoding in the through slice direction, but then what we care about are the kind of, the term, like, there's a linear term in this direction, which is, a cross term. We played in the through slice direction, but what's actually producing the field are the in-plane components. So yes, actually, when I talked about our preliminary like linear results, it is a cross term. Yeah. So yeah, actually the cross terms are very important to us. Yeah.
Well, thanks again, Mike.
Yeah.
Any other
awesome, yeah,
questions in the audience? And we'll say goodbye to Mike and Shopping.
Sorry.
Connect you with Mike as well off.
Great. Yeah. Thanks for having me. Sorry I couldn't make it, everyone. Bye. Have a good one.